Okay. Um, so, yeah, a couple of things before I start. The first thing is about, I'm not going to put a deadline on questions from assignment 2 and assignment 3 because in a certain sense there isn't time. What I want is the students to have done a roughly equal number of questions from each assignment. Okay, and so in particular a good number of questions from the final assignment as well as from assignment 2. Now, I don't want to be more specific than that because if I do that, then I'm committed to it. And if I say you've got to do 15 and somebody does 13, then I've got to do something I want to do. So if you're not sure about what's going on, you can always ask. But anyway, so what I'm asking for is a roughly equal number of, ideally I'd like a roughly equal number of questions from each assignment. Now the first assignment's already gone, so you don't have to worry about that, but make sure you do a good number on assignment 3 as well as assignment 2. And it's no problem for me if you just go through and pick the easy questions first. In fact, you're silly if you don't. Are there any questions about that? The other thing is there's more than my usual share of typos and mistakes in the last set of notes, lecture notes. I corrected them before I posted them, so the posted notes should be better. Well, what happened was I proved this string of inequalities, this string of homomorphisms. So it might be worth reminding you, these are the unit vectors, the flat unit vectors in CM, and these are the unit vectors in CM, and this is the unit arrangement, which I won't define again. And then from that, I get this chain of inequalities. Okay, there's actually a little bit of work involved to prove this one, but I get this chain of inequalities, and I had the signs wrong. So this is the, so you can, yeah. Now, the reason this is important is because we can use this to get an upper bound on the rank 1 chromatic number, and that bounds all the other ones. So this gives us another bound on the quantum chromatic number. And so if we can show that this inequality is strict, we've established that the quantum chromatic number in that case is strictly less than the classical chromatic number. Okay, so in a sense, it's this inequality which really matters to us. Now, the example I was using was, I think actually, no, so I'm going to demonstrate that in much of today's lecture. So where I'm going to work with the, I'll call it 5n, the graph with the plus or minus 1 vectors of length n as vertices adjacent if they're orthogonal. So it's a induced subgraph of omega of n. But it's only using the plus or minus 1 vectors. And now they should be scaled, but it's easy to deal with that. So I'm not, I should multiply by 1 root n or something, but I'm not, when I say unit vectors, you have to interpret the word unit properly. So there are a few remarks. So we're going to be concerned with the chromatic number of this graph. The first case is easy. If n is odd, then this graph is empty. And I went through the reason this last time. If you have plus minus 1 vectors, you have your once vector. Okay, and anything orthogonal that must have an equal number of 1s and minus 1, so it must have even length. So that's easy. This is slightly more complicated. If the number of vertices, if n's congruent to 2 mod 4, then this graph's bipartite. I might put that down as an exercise, although it's not much harder than the first one. Then the I claim if n's divisible by 4, then the size of the largest clique is at most n. Now the graph's got 2 to the n vertices, just to remind you here. So the point is that the maximal cliques consist of a set, any clique consists of a set of pairwise orthogonal vectors, and the largest size of a set of pairwise orthogonal vectors in CDN is n. So the maximal cliques have size of most n. And in fact, since we're using the plus or minus 1 vectors, the maximal cliques are Hadamard matrices. Now, I'm not sure we define them or not. So Hadamard matrix is n by n plus or minus 1 matrix, and H transposed H equals n times the identity. Now, there's also a complex version of this, which is also important in physics too. So Hadamard matrices, I talked about them last time. The conjecture is that if 4 divides n, there is a Hadamard matrix, but that's open, and I think the smallest open order is still less than 1,000. Now, so it's immediate that because of the inequality that I was throwing out earlier, that the rank 1 quadratic number of 5n is less than or equal to zeta flat of 5n, and that's n. Okay, we've got an embedding in we've got an embedding in the flat unit vectors in dimension n. So we have that the rank 1 quadratic number is most n. Okay, now note that if there's a clique of size n in the graph, then the actual quadratic number is at least n, and so that would imply that so if there's a clique of size n in the graph, then you can show that the quantum quadratic number must be at least n. Okay, so what we're heading to show is that the quantum quadratic number is exactly n. Okay, now there's another piece of information which we need. The maximum size of a co-clique in omega n is bounded above by 2 to the n on n. Now, this can be proved by the ratio bound, but it means you've got to be fiddling around with eigenvalues and eigenvectors in the Hamming scheme, and I've chosen not to do that. So I'm just going to cite it to you. So the point is you can work out the least eigenvalue of phi n, and when you do that, you get this bound, the ratio bound. And that's going to play a role. Okay, so what we aim to prove is that if 4 divides n and n is at least 8, then the quadratic number of phi n is greater than n. Okay, and the fractional the rank 1 quadratic number is n, so we have our gap. Now, in fact, the gap is exponential in size. The other point is that if this inequality is tight, well, the right-hand side has to be an integer, and so n must divide 2 to the n. Okay, and we're going to see that the only case where we have problems is when there's inequality. The only case we need to deal with is when the inequality is tight. And so in that case, n itself must be a power of 2. Okay, here it is. Now, the next thing is if n is a power of 2, or 2 to the k, then this matrix, the conic product of A copies of that matrix, is a Hadamard matrix. Okay, size 2 to the k by 2 to the k. Okay, so if n is a power of 2, there is a Hadamard matrix. Okay, so there are integers m such that we don't know whether there's a Hadamard matrix of order 4m, but definitely if n is a power of 2, there are Hadamard matrices. Okay, in fact, the hard cases, the open cases you're going to have to deal with something of the order of 4 times p, but we're Peter prime. Anyway, so if we're dealing with 5n when n is a power of 2, then the clique size is n, because this matrix is sometimes called the Sylvester matrix. Okay, and so we have we know the clique size for our graph. Now to prove the theorem, we actually need some results on Cayley graphs. And I've got a comment here, note that phi n is a Cayley graph for z2 to the n. Now, I'm going to set this up as an exercise, but the thing to notice, if you change the sign of the ith entry so the vertices in phi n are possible H1 vectors of length n. If you change the sign of the ith entry, that gives you a permutation of the vertices. Okay, and that permutation is an automorphism, and that operation preserves orthogonality. If 2 vectors were orthogonal before you change the sign, they're orthogonal after you change the sign. So that gives you an automorphism in the graph. And so you've got n automorphisms of order 2, and you can show they generate the elementary abelian group of order 2 to the n, and you can show the whole graph is a Cayley graph for that. So it's not difficult. Well, I shouldn't say those sorts of things, but I don't think it's difficult. Now so we're proving. So we have alpha the maximum size of a co-clique, and omega the maximum size of a clique. And things like this are often referred to as clique co-clique bounds. And these are very important. They come in lots of applications. But the right context for treating these as association schemes, and I'm not going there. So I'm just going to work out the bound that I actually need. And so we're saying that we have this for a cardiograph. So let's think about the proof. The proof is, suppose S is a co-clique in X and A and B are adjacent. Then we're going to look at the translates of S inverse. So S inverse is the set you get by take S as a subset of the group. You take the inverse of each of those elements, you get S inverse. And the claim is that these sets are pairwise disjoint. If A and B are adjacent, then these are disjoint. Okay. Now, so that will then immediately imply this. Okay, so we just need to show they're disjoint. Now, if they're not disjoint, then there's a element G and H, elements G and H in S, such that G inverse A is equal to H inverse B. Okay, where G and H are in S. And so now I'm just doing the obvious rearrangement. So I'm bringing the H over here and the A to here, and I get this. Now, since G and H are in S, they're not adjacent because S is a co-clique. And so that if I definition of cardiograph, that implies that HG inverse is not in the connection set. On the other hand, B and A are adjacent, and so this is in the connection set, and so this is wrong. So we conclude that I don't know if I read it down, we conclude that if S is co-clique, excuse me. Then the translates sets the form S inverse C are pairwise disjoint, and that gives you a lemma. Okay, so that's easy. You can turn this into, this actually implies that the same thing is true for vertex transitive graphs. But there's an argument in my book with Gordon that lets you deduce, will let you deduce the general result from this. But I'm dealing with 5N. It is a cardiograph, so I don't need to go and worry about what happens in general. But there are some more general versions of this are true. Okay. I haven't done with cardigraphs yet. So I say a cardiograph is normal if its connection set is closed under conjugation. Now, I should warn you that there are people who work on cardigraphs for a living, and they will use the word normal to refer to something else. Now, I've been working on these things as long as they have, so I'm not happy enough to stick with this. So just warning, in the literature, there are two usages of the term, and in particular, people working on ordinals and cardigraphs and things, they won't use this particular usage. But anyway, leave it at that. So cardiograph is normal if its connection set is closed under conjugation. Now, the simplest example is when the group is abelian, because then the conjugate of an element is itself. Okay, and so any cardiograph for an abelian group is normal. And we're dealing with a cardiograph for Z2 to the K, and so Z2 to the N, and so we're dealing with a normal cardiograph. Now, normal cardigraphs have some nice properties that other graphs don't have, and so we'll give that. So what we're going to prove is that if cardiograph is normal and our inequality, our co-clique inequality was tight, then the chromatic number is equal to the clique number. Okay, which is a nice result. So we assume again that we've got a co-clique S and a clique C in X. And as before, the sets S inverse C for C and C are pairwise disjoint. But the claim is that S inverse is a co-clique. Now, S is a co-clique, but the inverses don't have to be. And I don't come prepared with an example. And if you ask for one, I'll put the question on the assignment. But so the point is that S is a co-clique, but it does not follow in general, but that means that S inverse is a co-clique. But in this case, since the K-graph is normal, it will follow. So we're using normality to get the sets S inverse co-cliques, and then that will give us this result. Okay, so I was using D for the connection set. And so if G and H are in S inverse and G are adjacent, then HG inverse is in D. And now I'm taking a conjugate of that and conjugating it by G, and I get G inverse H. So it's a conjugate of HG inverse, and so that is in D. And that implies that H inverse is adjacent to G inverse. So so that gives us a contradiction, and we conclude that if equality holds, then the sets S inverse C give a proper coloring. Okay. So the so it follows as shown that the correct number of phi n is greater than n if n is not a power of 2 but divisible by 4, and if the correct number of phi n is n, then the size independent set is 2 to the n on n, where n is necessarily a power of 2. Okay. Now to finish through it, so the point is the only way I can get chromatic number n is to have alpha of this size. Okay, my cliques have size n, so if I'm going to get chromatic number n, the co-cliques have to be this size. Okay, and there's a deep result of Frankel and Rödel which tells us that there's a positive real number of epsilon such that alpha of phi of 4m is less than 2 minus epsilon to the n. Okay, and so that tells you that the chromatic number of phi of m grows exponentially with m. Now, this is a result of the probabilistic combinatorics, and the paper has got a number of significant applications. This is one of them. Proving this is about the same difficulty as proving this slightly more general result. But so they have that general result, and we're using it. So this is not trivial in any sense. I haven't actually worked through the proofs there in any detail, but it's there. It's an important result, and as I said, a deep result. So that tells us that the chromatic number of phi of n increases exponentially with n. Okay, whereas the quantum gradient number is constant equal to n. Okay. And so that gives us our class of examples. And we're going for time. Okay, so the problem with that, well, the physicists, of course, were interested in working out what the smallest value of n was for which phi of n had the quantum gradient number was bigger than the classical chromatic number. And Mike Newman proved that that started at 16, so that so phi of 16 had chromatic number greater than n, and it increases as you go on. So Frankel's result tells you that if n is large enough, you're okay. But in fact, n being large enough is n is at least 16. Okay. Still, that means you've got a graph on 2 to the 16 vertices, which is something of the order of 64,000. And so at that point, you might ask for possibly there are smaller examples. Okay, and that's what we'll turn to next. Now the construction there, we're going to do this involves quaternions, and so I'm going to go on about quaternions for a while because it's a useful thing to do. So the quaternions are the 4-dimensional algebra over the reals. They've got a basis 1, I, J, and K, satisfying the first mistake. I squared equals J squared equals -1. and the relations ij is equal to k, jk is equal to I, ki is equal to j. Notice that I'm rotating ij and k cyclically, and I get those three things. Now, these relations imply that ji is equal to minus k and jk is equal to minus I. And so if you change the order of two of the base elements, or if you have, okay, so ki is equal to ji, k is equal to minus j. So that's a consequence of those relations. So the point here is that an algebra is a vector space. Sorry, is a ring with a field sitting in its center. Okay. Now we've defined our ring. We said we're generated by elements 1, I, j, and k, and we've got certain relations. So that defines the algebra. Okay. The trouble with that definition and in fact, that's a sort of a standard way of defining an algebra. The trouble with that definition is that, generally speaking, if you're just given the generators and some relations, it's very difficult to work out the structure of the algebra. Okay, I mean, in group theory, I can write down, do the same thing for groups. I write down some generators and relations. Deciding whether the group you get is trivial is undecidable. And algebras aren't going to be any easier. Okay, so anyway, so the point is these relations do define the algebra. Now, of course, we want something more convenient. Well, I've already hinted at it. We're going to have a four-dimensional vector space over the reals, and we've got our basis, 1, I, j, and k. Okay, so that's well and good. And the comment I want to make is that the quaternions form what is called a skew field, which is a non-commutative field. So it has all the distributivity and associative axioms, but it drops the commutativity. Sometimes the geometers are referred to as division algebras. So we'll stick to skew field for now. Okay. Now, so I want to understand, basically what I want to do is show that the quaternions norm 1 are isomorphic to the orthogonality graph on the quaternions norm 1, which I haven't defined properly yet, is isomorphic to the unitary derangement graphs over C4, over R4. Okay, and so that will give me my information on the coloring, but we're not anywhere near that yet. So we're trying to understand, we're trying to get to that point though. So if I have a vector x in R to the 4, then I can define a quaternion in the obvious fashion. Oops, I don't want to do it that way. I want to, yeah, so we can define a quaternion. Okay, so now we have that gives us a bijection from R to the 4 to quaternions. Okay. Now there's a second operation we want to define, which is the conjugate. Yeah, we'll put that in. And so that you just change the signs of I, j, and k. So if you're working with the complex numbers as an algebra of the reals, then this would just do normal complex conjugation. You should also note that the quaternions are not an algebra over the complex numbers, because the element, if you say I'm going to take 1 and I to generate the complex numbers, I is not in the center of the algebra. Is not in the center of that algebra. It doesn't commute with j and k. So you do not have an algebra over C. You have an algebra over the reals. Okay. So it's true you've got an algebra and it contains a copy of the complex numbers. And all I'm saying, it's not an algebra of the complex numbers, it's an algebra of the reals. Similar thing that the Hermitian matrices and matrices complex interest, they form a real algebra. They don't form a complex algebra because I times an Hermitian matrix is not Hermitian. Okay, so we have this conjugate map, which is an anti-order morphism of H, so it reverses the order of multiplication. Now, the couple of terms, the trace of a quaternion is twice the value of x0, and we say that the quaternion is pure if the trace is 0, so the x0 term goes away. And if you check, you'll find that q star x minus qx is equal to x, x1 squared. So so unit vector, well, Yeah, okay. Now, this is called the norm of the quaternion. It doesn't look like the norms we're used to. There's no square roots around. The point is the terminology is really coming from number theory. And so the number theory setting, this would correspond to the norm of an extension. This would correspond to trace. Okay, so it looks a bit funny in this language, but it's because you're inclined to think it in terms of algebra, operator theory and the algebra, but it's actually the terminology is being driven by number theory, because quaternions play quite a significant role in number theory. Okay, but anyway, it doesn't matter to us. So we've got trace, it's twice x0. So the trace is x plus x starred, and the norm is x times x starred. And so we call this the norm of quaternion. Now, if A is a quaternion, we have a linear mapping, I'll take a note by mu sub A, which sends any quaternion x to A times x. Now, it follows from this that any non-zero quaternion is invertible. Okay, so okay, so now we've got a linear map from quaternions to quaternions, and so a linear map from a four-dimensional space to itself. And so as a traditional, the next step is to ask you to work out the matrices running this map relative to a basis. And the only basis inside is 1, I, j, and k. Okay, so I abbreviate things a little bit here. Clearly mu0 is just the identity matrix. Okay, so that's actually multiplication by 1, but I don't want to use, maybe I could have called it mu1, doesn't matter, 0 now. So mu I is multiplication on the left by I, so it sends 1 to I. And so the image of 1 is 0 times the first term of the basis plus 1 times I plus 0 times j plus 0 times k. So 0 times 1. Okay, and so you go through and you work it out. And I didn't bother with the transpose. I probably should have. Technically, yeah, it's the transpose of this. Oh, well, I can fix that. So this is the matrix that represents multiplication by I. Notice it's got the square of it. So that rules out the possibility, some of the possibilities of mistakes. So you can now go through and do the same for j and k. And these should again have transposes if I care. And again, you can check that each of these matrices has got order 2. It's fairly obvious for this. I might need a moment's thought for that. So we have 4 matrices, four 4x4 matrices representing our, we're representing the quaternions. Okay, so what's happening, we have a map from the reals into the quaternions. And what I'm constructing is actually a map from the quaternions into the unitary group of 4x4 matrices, because I want to play with my unitary derangement graph. Okay, so I've got the 4 matrices there, and so I copied this from somewhere else. And so if I work out mu for a general vector x, then I get this. So it's you get there's the 0 entries. The 1s are here and here, and the 2s are there and there, and the 3s are down the backwards diagonal. So now I have a map. This is the linear map from R4 into quaternions. Okay, and the couple of things. If you look at the diagonal entries, if this is x, this is what mu of x. This is mu of y starred. The diagonal entries that are 0. Okay, if and only if x transpose y is 0. So if x, so I have a map takes x to a quaternion, y to a quaternion, and x and y are orthogonal if and only if x transpose, if and only if mu x, mu starred y has 0 diagonal. But that's what I want. That's the unity derangement. And so we have a map. So we don't just have a map from R4 to the two 4x4 matrices. We actually have a map from the orthogonality graph on R4 to the unitary matrices, and that sends the orthogonality graph to the unity derangement graph. Okay, so the summarize, if we use omega sub r to denote the unit vectors in RBN, then we've established there's a homomorphism from the omega R4 to the unity derangements 4, and it's a homomorphism. And so adjacency here is orthogonality, and adjacency here is that xy star is pure. The diagonal is 0. Okay, so and so that then implies that the rank 1 chromatic number of the omega R4 is 4. So any questions about that? Okay. Now I should say this material we're covering comes from a paper by who is it? I'll give you a few of the names. You can look up the rest. There's Cameron. Oh, I'm going to forget one. I'll put in enough that you'll be able to find it on Zoom. Newman, Severini. And so this example was worked out there. Now, as I said, the challenge is to get a smaller graph with where the chromatic quantum gradient number and the chromatic number are different. In this paper, they gave an example of a graph on 18 vertices. I think there's a tradition in these papers to get the diagrams wrong, I should warn you. Subsequently, Manchinsky and Robertson came up with a small example on 13 vertices, which I'm going to talk about now. So we're going to take, so I'm going to construct an orthogonality graph on these 13 vectors. Well, there they are. There's 13 of them. In the paper I'm copying from, there are only 12, but there needs to be 13. Now, I'll go where these come from in a moment. Now, so the point is that I've given you those 13 vectors in R3. Okay, so I can construct an orthogonality graph, and I'm calling that graph G13, because that's what Manchinsky and Robertson did. And it was subsequently proved this is going to be the smallest graph for which the classical and quantum gradient numbers are different. Okay. Now, I need an additional comment. If you add a bottom row of zeros to this, so you get a 4x13 matrix, and then add an extra vector, 0, 0, 0, 1, then you get a new graph, and that new graph is the cone over G13. So you take a new vertex, this guy, and you make it adjacent to everything in G13. Okay, so that's G14. I didn't waste any time on the names of these graphs. Now, the point about whatever if G has got 13, it's got chromatic number C, then this guy's got chromatic number C plus 1. Okay. The amazing thing is that G13 and G14 have the same quantum gradient. So not only is there a difference qualitatively, there's a difference in behavior. And so you can ask for examples of graphs where the quantum gradient number is different from the classical gradient number. You could also ask, when are the graphs, when can you take a cone and not change the quantum gradient number? And I don't think anybody's even raised that question. So what do we know about G13? Well, the correct number of G13 is 4. And in the paper, they give an argument. And I really don't care. You just stuff the graph on stuff the graph in the computer and ask it, get the crank number. 13 vertices is not so big, you get into trouble. It's somewhat surprising that the computing crank number and computing the alpha, the size largest co-clique, are both NP-complete problems, and so they're equivalent in the complexity sense. But in practice, the computation of large co-cliques is easier than the computation of crank number. Now, no explanation for it. So I mean, if you're for a computer science, if you're a computer science working complexity theory, then those two problems have the same difficulty. Well, that may well be true in that sense, but in practice, you can get co-cliques in graphs on hundreds of vertices, whereas you can get stuck on crank number in graphs on 40 vertices. But 14 is not so big. 13, 40 is not so big. Now, if the crank number of G13 is 4, then the cone's going to have crank number 5. Okay. Now, what we're going to prove using the stuff we did at Quaternions, or follows what we did there, is that the rank 1 crank numbers of these two graphs are less than or equal to 4. Now, since I'm talking about references, there's a Manchinska, and I'm going to get the accents wrong, so forgive me, and Roberson have a paper saying on the lines, all of these are quantum colorings. Now, and they give proofs that of this, in fact, the crank number is not 3. This was proved earlier by a non-trivial computation, and then Laura and David give a proof that takes a couple of pages. And the thing to notice here is we don't have very much machinery for determining quantum crank numbers. I already said determining chromatic numbers is hard, and quantum crank numbers are certainly no easier. Okay, so these are the facts that we have. So the point is that, well, sorry, what do I write next? Yeah, so G13 is an orthogonality graph in R3, and R3 sits in R4. Okay, and we have the homomorphism from the orthogonality graph on R4 into the unitary derangement graph. That's 4 by 4. Actually, the orthogonal matrix is not just unitary. Into the unitary derangement graph, and so that implies that the chromatic number, the rank 1 chromatic number, is at most 4. I should also say that this trick with the quaternions, if you've heard about the quaternions, you may have heard about the octonions, which are an 8-dimensional algebra, which is no longer associative. And using the octonions, you can prove things like if you're in the orthogonality graph in R8, the orthogonality graph for R8 is isomorphic to the unity derangement, or actually the orthogonal derangement graph in 8 dimensions. So the theorems, the stuff we're studying for 4 can be extended to 8. But I've got no intention of trying to play with octonions here, and there's no real point. The next question, of course, well, I don't know where Dave and Laura came across it, why they picked on this graph. It's actually a good thought. So where does it come from? Well, in fact, it's got a name. It's a so-called Erdős-Renyi graph. Now, the point to be careful about here is that if you Google on Erdős-Renyi graph, you will get information about the random graph, where you take n vertices and you join a pair of vertices by an edge with probability p. And I had a quick look yesterday. I had a bit of a look yesterday. I didn't spend too long on it, but I went past the first page, and I did not find a reference to this particular graph. Now, it is called the Erdős-Renyi graph. It's well known. It's got that name. But if you Google, you're going to pull up the stuff about the random graph, which is not what we're talking about. Okay, so the different graphs. Okay, now to construct it, you choose a finite field of order Q, odd order, the vertices of the graph are the one-dimensional subspaces of the three-dimensional vector space over F. So if the field's got order Q, then the three-dimensional vector space has got order Q cubed, and it has Q cubed minus 1 non-zero vectors. And each one-dimensional vector space contains Q minus 1 non-zero vectors. And so you get Q cubed minus 1 over Q minus 1. And so you get Q squared plus Q plus 1. So these are, you can view these as the points of the projective plane of order Q if it helped you. But anyway, we're not going to do that. So we're just saying we take the one-dimensional subspaces of the three-dimensional vector space over that field. And two one-dimensional subspaces are going to be adjacent if their dot product is 0. Now, you have to be a bit cautious within the product over finite fields. But anyway, well, there aren't any products. But this is but anyway, with X transpose is still defined, so this still makes sense. Okay, so that gives a graph. Okay, and that is the Erdős-Rényi graph, and so we get one for each finite field of order Q. Now, as just defined, this gives you a Q plus 1 regular graph on Q squared plus Q plus 1 vertices. You have to work a bit to prove that. It's not too hard. The only complication is you discover that Q plus 1 of your vertices have loops. Now, if a graph has a loop, you can't color it with any number of colors because you can't assign a color. If vertex I has got a loop on it, then whatever color you give it, you've now got an edge, that loop, with two ends of the same color. So if you're after coloring, then you don't want those loops. And so the simplest thing to do is just throw those loops away. So now the graph is no longer regular. It's got the vertices of valency Q and vertices, actually Q plus 1 of them, and vertices of valency Q plus 1. So there's Q squared vertices of valency Q plus 1 and Q plus 1 of valency Q. Now, this is not a particular problem. It's just, okay, out in the real world, we've suddenly discovered there are loops around. We don't want them, so we throw them off. Okay, so we get a graph. Okay, and if Q equals 3, then the graph you get is the G13. Now, the Erdős-Rényi graphs, the reason that Erdős and Rényi were interested in these things is because they're graphs with a large number of edges and no 4 cycles. Now, I don't think that's important for us, but that's why they were interested. They had lots of edges and no 4 cycles. Okay, and they got a lot of symmetry because you're basically dealing with the projective plane of order Q. Now, Maria Sobchuk proved that if you if Q is an odd prime, then you can again get graphs with chromatic number different from the chromatic quantum grank number. So this observation leads to a generalization of their result. Now, so you have an infinite family of graphs where the quantum grank number and the chromatic number differ. Okay, they'll only differ by 1, and that's all right. Any questions at this point? I might make the comment. I mean, I'm pretty sure that Dave and Laura did not. It seems that Dave and Laura did not recognize this was an Erdős-Rényi graph. There's no particular reason why they should, but they didn't. Okay, and it's kind of interesting that you're looking for these nice examples, and you're forcing into something which is in some sense a classical combinatorial structure. It's turned up in other places. There's many papers on them. Okay, so that's the example. So I've done that. Now, so the next step. Well, still, we'd like to get more information about when these two parameters, the chromatic number and the quantum grank number, differ. And to do that, it'd be nice to we want to have some bounds on the parameters of interest. Now, I'm starting. What I got here is a list of some bounds on classical parameters. So there's no Q inside at this point. Okay. Now, some of these bounds we're going to generalize, but I just wanted to write. So here are 4 classical bounds. The first thing is that the ratio bound for co-cliques. Okay, we proved that back in the first part of the course. Okay, number of vertices over 1 minus k on tau, and that holds for regular graphs. If the graph is one walk regular, which you've forgotten what it means, but which I discussed earlier, so arc transitive, for example, then the maximum size of a clique is 1 minus k on tau. So it's the same term. And so that's why I refer to these as ratio bounds. Now, it is interesting that although these bounds are closely related, so we know that if the graph is a K graph, then alpha x times omega x is less than or equal to n. And so this will tell us that if the graph is one walk regular, then alpha x times omega x is less than or equal to n. Which is a weaker result than what's actually true, but we won't go there. Now, the other thing is that it's still a surprise to me that you need a stronger condition on the graph to get the clique bound than you needed to get the co-clique bound. You'd sort of think, well, I have a bound on co-cliques. I just take the complement, and that gives you a bound on cliques. And that seems not to be a useful strategy. Okay, so there's similarities between what goes on with cliques and co-cliques, but there's also some differences. Now, there's a couple more bounds. I want to talk about this is what's called the inertia bound on alpha of x. And so it states that the alpha of x is the minimum of the number of non-positive eigenvalues and the number of non-negative eigenvalues. Okay. So the Peterson graph, exactly, for example, its eigenvalues are, sorry, more coming here, a 3, 1 with multiplicity 5, and -2 with multiplicity 4. So 4 times -2 is -8, 5 plus 3 is 8, so that's right, the trace is right. Now, so there are 6 positive eigenvalues and 4 negative eigenvalues. And so the inertia bound tells me that the size of the co-clique in the Peterson graph is at most 4. And that's tight. Okay. For the Peterson graph, you also get tight from the ratio bound, but we won't go there. Okay. The last bound is one we'll be talking about most, and this is generally called the Hoffman bound. This bound is also often ascribed to Hoffman. The situation is a little bit more complicated because in most of the cases where we actually use it, the bound follows from an earlier result, but then Hoffman generalized it. So so I just called this the ratio bound so that people involved there were Hoffman, Delsart. We don't need to go with that. Now, so we have this bound. Now, the interesting thing about I don't need x as regular. Do it this way for any x. We have a lower bound on the correct number. Okay, now it's the similar form to the bound on the co-cliques. Sorry, bound on cliques. Okay, so if we have a one walk regular graph, then this is equal to that. And so you have a complicated proof that omega x is less than or equal to chi of x, and you might prefer to use simpler arguments. Question here. That's just references. So we have these bounds. Now, what I plan to talk about is this guy. Okay. I'm also going to, and the last two, in fact. So what's the time? No, I'm going to stop there. I'll also prove this for other reasons. Okay, so next lecture I'll start on bringing those bounds, but I'll stop now.